All right, so section 7.1, we are at the start of a brand new chapter. And what we are going to be studying in this chapter is something called the Laplace transform. Okay, and so today we're going to really start with this idea of what it is, where it comes from, but the rest of the chapter is really about how do we use it and more about the shortcuts. Okay. And so let's go ahead and start with what we know. And with what we know today is actually going to be rooted very much in limits and derivatives. So we're going to revisit some of your calculus, Calc 1 in particular, experiences. And so if you think back to when you first took Calc 1, at some point, in the beginning of the year, you were looking at something like this: the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And you took a look at this and there was a lot of algebra and you had to like crank through to figure out what this limit was. And it was sort of a strange gap between like looking at limits on graphs and then looking at this, and then all of a sudden moving to derivatives. But this right here is what we call the formal definition of a derivative. Okay. And so I don't know how long ago Calc 1 was for each of you, but this formal definition here was an important juncture in your mathematical career, because basically you set the stage for the idea of slope, right? When we think about derivatives, we're really thinking all about the slope of a function. And so what we have here is really the slope equation, but with 2 points that are really, really close together, right? That was the whole idea behind the limit approaches 0. The limit as h approaches 0 is that these 2 points are super close together. And if we have 2 points that are super close together, we can think about it basically as the slope at that point. Okay. And so that's why this piece was important. Beyond all the algebra that it made you practice, it was important because the concept was sort of this idea of 2 points really close together. But after you learn that, you were probably like, oh, thank goodness there's all these shortcuts, right? There was the power rule. What other rules do you know? Tell me about those rules you know from Calc 1 about derivative. You might not like them, but I know you know some rules. Yeah, there was a chain rule, good old chain rule, keeps coming up. Super, super common rule in differential equations, right? We've got the product rule. This is good. What other rules do we know? Yeah, if we know product, we know quotient, we hope. There was even implicit, where maybe like the x's and y's were all mixed together and you had to use the different rules and be able to find that derivative without solving for y first, right? And so these are some of the rules that you spent a lot of time on developing those skills in Calc 1, right? Power rule, chain rule, product, quotient, implicit, and all of this stuff has come back again and again, maybe to your delight or your dismay, I'm not sure. But what we're going to do today, okay, so why this is important is we're going to follow the same idea for this chapter, okay? So today, we're going to learn something that is the equivalent of the formal definition of a derivative. The equivalent in the sense that it's the formal definition of something, and that something is the Laplace transform. Okay, so we're going to start with a formal definition, and then the rest of this week and next week, we're going to learn a bunch of rules to help us shortcut what we learned today. Okay, so it's a much more accelerated version of this idea. And so that's why I would really want to point out the structure to this. Okay, so let's write that down in our what's new section. Today, we're going to be taking a look at the formal definition of the Laplace transform. And there is, I think, one question on your homework this week that asks you to use the formal definition. So I don't want to beat you over the head with the formal definition. I think it's important. We'll do a bunch of examples today, but as we know from what we learned in Calc 1, that's really more to set our understanding in the concept so that when we learn the rules, we understand that all those rules are shortcuts, okay? And so we're going to be using this to take a look at inverse transforms. We're going to be looking at transforms of derivatives. We're going to look at something called translation theorems. We're going to look at how this applies to transforms of integrals. And then we'll take a look at something called the Dirac delta function. Okay. So as you're sort of organizing things in your brain, okay, today we start here, and then tomorrow and the rest of this week and next week, we'll sort of go through all the things in the blue, okay? But they all come from the same concept that we're going to talk about today. All right. So there it is, a brief revisit to your Calc 1 experience and thinking about how what we're learning right now is actually going to be very much in parallel to what you learned before. Okay. All right. So the overview of where we're going. Let's say that we have a function, and we'll pick a very simple one for this case, f of x equals x squared. Now, every single one of you in here knows that if you take the derivative of x squared, you'll end up with 2x. And if you integrate x squared, you'll end up with x cubed over 3 plus c, right? We all know that. But why is that important? Well, it turns out that when we take the derivative is a transform, okay? It takes a function and it maps it onto a different function. So it takes x squared and maps it into 2x. Okay, so the derivative is a transform. Now, similarly, the integral is also something called a transform. Okay, now I think sometimes the vocabulary makes things sound much more intimidating than they are, but especially if there's anyone out there who's looking to be, you know, a math major or a math minor, the idea of the vocabulary and just making sure you understand the story is actually going to be so key to your success. Okay, so don't let the vocabulary scare you, but rather use that to say, okay, what is this story telling me? And so the story of the derivative is that if I take a function like x squared, I can map it to a different function, 2x. And the story of the integral is I can take a function, say x squared, and I can map it to a different function, x cubed over 3 plus c. Okay. And so even if you're thinking, oh, a Laplace transform sounds so intimidating, it's basically another kind of function like this that takes one expression and maps it to another expression. Okay. And so this Laplace transform, let's actually write out what that looks like. Okay. So to use the Laplace transform, the symbol we use is a uppercase scripty L. Okay. So in other words, we do something like this. All right. So I would practice, you know, like we see all these Greek letters, I would practice how you choose to write them, but this scripty uppercase L means Laplace transform. Okay, and we're going to be using that quite a bit over the next 6 or 7 days. Okay, and so if we want to apply a Laplace transform to a function, we actually put the function inside curly braces. Okay, so we put the function, we'll say f of t, inside these curly braces. All right, so I'll just give you a moment to kind of practice that, your uppercase script L with the curly braces and your function, which is a function with respect to t on the inside. Now, the definition of what we mean by a Laplace transform, it is actually based on an improper integral. And so this is where we sort of very briefly revisit Calc 2 and we think about improper integrals, which if you're trying to think back into your brain when that might have happened, it was probably around the same time that you learned about L'Hopital's rule and all the other indeterminate forms. This is sort of revisiting that point in your mathematical career. And so the formal definition of the Laplace transform is that it is an improper integral going from 0 to infinity. And so it's improper because one of the bounds is infinity, of e to the negative st times f of t dt. And what this says, right, this middle chunk right here, is that this is a Laplace transform of f of t, provided that the integral converges. Okay, so this is what we define the Laplace transform to be, but only when the integral converges. All right, and so we really want to think about that convergence idea as basically we're approaching a numerical value. Okay, meaning that we can approach a value of like 2 or -1 or pi or e. We can get to an actual number. In other words, the system, like whatever we're looking at right here, it doesn't blow up. Okay, and so it's sort of the mathematical equivalent of a system blowing up is when something, the limit of that of something approaches infinity or it approaches negative infinity. Those are problematic for us. Okay. But another important piece of notation here, if we think about when we usually say the integral of something, we then take that whatever function. So let's say we had lowercase f, now we replace it with an uppercase f of the new letter that we're replacing it with. Okay. And so this capital F of S, what does this mean? This part is called the transform. Okay, so capital or uppercase F of S is the transform. And a transform is nothing, it is a function, right? So it is a function of a new variable. So we'll notice here that this letter inside the parentheses is not a t anymore, right? So we started with f of t, lowercase f of t, and we're ending up with uppercase f of s. There's no more t in that final answer. So a transform is a function of a new variable s, and all of the t's will drop out in the process. Now, I do want to make one quick note right here about this integral. And some folks might be wondering, like, why are we starting at 0? Why don't we start at a different number? And it turns out that this is working under a particular assumption, okay? Because remember, a lot of differential equations is applied, meaning that you're using it to solve real world problems. And so we might have an integral from negative infinity to positive infinity. That's like more truly what we think about when we're looking at an improper integral of e to the negative st times f of t dt. But this version that we have in our Laplace transform assumes that f of t is actually a piecewise function that's defined as the following: that for t greater than or equal to 0, right? And again, if we're thinking about an application, like we don't usually think about negative time. We think about when does time start? Whatever that time is, we say that's t equals 0, right? And so we're saying that our function is really defined for t greater than or equal to 0. Otherwise, if t is less than 0, we say that the function is defined as 0. Okay, and so that's why we actually choose to start with this 0 in our formal definition of the Laplace transform, because we're saying no matter what the function is, we really only care about the part of the function that is after t equals 0 and after that point. Okay. And so let's get that overview for you all on one page. But today will be a day where we revisit so much of our improper integrals and lots of integration before we move into the shortcut rules that we'll be looking at tomorrow. Okay. All right. So let's go ahead and take a look at some practice. Okay. Now, this first one right here, all right, let's just kind of revisit what it means to take an improper integral, okay? Because I think that's sort of been a long time ago. So we're really looking at this to say, what is an improper integral? Refresher. I see a question in the chat. What does the Laplace transform represent? That's a really great question. And so what we're going to see as we move through this, okay, but sort of as a sneak preview, we're going to see as we go through today that like all of the calculus that we've learned up until this point, we can do all of these things that we're going to do using calculus that we know, meaning integrals, improper integrals in particular. But the long game of this is that the Laplace transform is going to allow us to take differential equations, take the calculus out of the differential equation. We're going to turn it into an algebra problem. We're going to solve that problem, and then we're going to turn it back into a calculus problem. So the short story here is that the Laplace transform will help us solve differential equations. So it's another tool in our toolkit of how we solve differential equations, but helping us prepare for some equations in the future where maybe the calculus we know is just very long and very cumbersome, and the Laplace transform might be an easier, more efficient way to solve that particular problem. Okay, that's a great question there. All right. So let's do this improper integral refresher right here, okay? And so we are gonna go ahead and say, for this particular, that's actually a typo, that's supposed to be a C, okay? So the integral from 0 to infinity of e to the ct dt. And for this situation, we are going to assume that C is a constant and that C does not equal 0. Okay, so we're going to assume that C is a constant and it does not equal 0. And so if we think about the improper integral technique that we learned once upon a time, okay, if we take we have a continuous function, which e to the power of a variable is a continuous function. And we have one of the bounds is infinity. The equivalent statement of that is actually that we can say, let's take the integral from 0 to some letters, let's call it n, of this function. All right, so we'll pretend that that top bound is a number. But then we're going to say afterwards, let's consider what happens, the limit as that number approaches infinity. Okay, so we're really sort of taking the bound and let's say the bound is a problem. So let's pretend the bound is a number. And then afterwards, we'll take that limit as that bound approaches infinity. Okay. And so if we take this integral right now, so let's keep the limit as, I don't want to write it that way, sorry. Let's keep the limit as n approaches infinity. That part stays. But the integral of e to the ct is going to be 1 over c e to the ct, right? We're using the u sub and we're plugging in n and we're plugging in 0, right? And so again, let's keep that limit in the front. We haven't used it yet. And now we're going to plug in our bounds and see what we get. So we should get 1 over c e to the nt minus 1 over c e to the 0 times t. And we've seen this very frequently. We know that e to the 0 is just going to give us 1. And so what are we left with? We really have the limit as n approaches infinity of 1 over c. And we have e to the n. That's not a t, sorry. C, nc minus 1 over c. All right. Now, if we think about when this converges and when it diverges, okay, we might realize that as n gets really, really large, okay, we have an exponent that is getting bigger and bigger and bigger. And what that means in terms of like our system blowing up versus not giving us a number, okay, is we need to consider how we can sort of use C to fix what's happening in our system. In other words, if C is greater than 0, okay, if C is greater than 0, n times C is going to get really, really big. So if n is greater than 0, then the function diverges. All right. And again, it diverges because this exponential, the exponent itself gets really, really large. And we know that our exponential function looks like this, right? So as the x values or the input values get larger, the output gets really big, really fast. So then we say, well, what about if C is less than 0, right? And we don't want to say equal to 0 because we already said in the beginning that C is not equal to 0. And it turns out that if C is less than 0, then the function converges. And in particular, this part will go to 0, and we're going to end up just with -1/c. Okay, so let's get that all on one page for you. But that is a little bit of a refresher on what we mean by these improper integrals, okay, walking through that process. But let's see what the implications are for what we have in the questions that we're going to be taking a look at, okay? And so again, keep in mind that today, even if it's very like nitty gritty in the calculus, is really about setting the stage for why we have all these shortcut rules and where all these shortcut rules that we're going to learn tomorrow come from, okay? So there will be a table that we talk about tomorrow that will make your life much easier. But for today, we're going to sort of grin and bear it on this Monday morning. Okay. All right. So let's take a look at this particular question. All right. This is for some reason, the equation editor that I'm using does not have the Laplace symbol in it. So this is the best I could do. But really, this is the same as that uppercase script DL. Remember, for the Laplace transform, we use curly braces, and then we put the function inside of it, right? So uppercase script DL, curly braces with a 1 inside of it. And so we're going to find out what this equals, but we're going to use the formal definition, okay? So from above, we know that the Laplace transform means that we're going to take the integral from 0 to infinity of e to the negative st times your f of t. And in this case, f of t is just 1. Okay. So this is my f of t, so I put it into the formal definition. All right. And so this is going to look very similar to what we just took a look at. All right. And so we know that if we have a bound that is approaching infinity, that is problematic. So we're going to sort of take this into 2 separate steps. We're going to take the limit as n approaches infinity, the integral from 0 to n of e to the negative st. We're going to go ahead and integrate here. So I have the limit as n approaches infinity. My integral is going to be a little bit different than what I had before. It's actually going to be negative e to the negative st over s. And I'm evaluating at n and at 0. Right. And so the reason why I have a negative sign is because this is negative st, whereas in the previous problem, I just had a positive ct. So we have to, when we do our u substitution, think about that extra sign coming in there. Let's go ahead and plug in our bounds. We have the limit as n approaches infinity. And now we're plugging in our bounds. So we get negative e to the negative sn over s, and then minus a negative. So I'm just going to make that a plus sign, right? Minus a negative of e to the 0, which is just going to give me 1 over s. Okay. Now, I will say this, we are going to be writing the letter s a lot. And so I would just put it on your radar that s sometimes looks like a 5 when we are writing too quickly, right? Just like t looks like a plus sign when we're writing too quickly. And so I've yet to find a way to really help me remember an S is not a 5. My T's, I have a little tail on them so they don't look like a plus sign, but I would just be really, really careful as you're going through. If you realize that you don't have any more variables, it is possible your S turned into a 5 at some point, okay? So just kind of keep an eye out for that in your brain. All right, so we have this right here in terms of our evaluated improper integral. And before we said, let me go back up here for a moment. Before we said that we sort of considered the two cases of C. If C is greater than 0, then our function diverged. But in that particular case, if C was less than 0, then the function did converge. Okay. And so let's think about in parallel what happens over here. Okay. So over here, if S is, let's say, greater than 0, and then let's separately consider if S is less than 0. All right. And so based off of what we saw in the first problem, I'm wondering what we think, which one of these cases might be divergent in example 2. Right? They're super similar. So where might one be divergent based off of what we saw in the first example? Yeah, we're actually going to have it switched, right? Because the only difference is that the first one, we assume that C was, like, if we look at our integral, this one is like a positive one with the E term. And then this one is a negative one with the E term, right? And so what that means is that in this case, if we plug in a negative value, right? Negative, negative will make that exponent positive. And when that exponent gets positive, we're going to end up with a situation where that is going to go ahead and just blow up the system. Okay, so if S is less than 0, then the function diverges. All right. However, if S is greater than 0, then let's see what happens. E to the negative ns is going to approach 0. Okay, so this will go to 0 if the actual exponent overall is negative. Okay, and so what are we going to be left with? We're going to have the function converges to 1 over s. Okay. So again, we're going to have sort of this first clump go to 0, and we'll end up with a value, a y value, so to speak, of 1 over s. Okay. Now, all of that is to say, tomorrow, when we look at the table, one of the things we're going to see is that the Laplace transform of 1 is 1 over s. Okay. So when we see, when we see the table tomorrow, we'll see on the table, Laplace transform of 1 is 1 over s. And so I don't want us to just look at that and be like, great, someone just told me that it equals 1 over s. Let's think about where it came from, right? And it just comes from that formal definition, sort of the long way to get there. But starting tomorrow, we'll be able to just look at the table and say, oh, I have a 1, that's going to be equal to 1 over s. Okay. All right. So let's keep moving. Let's take a look at some more variations with this formal definition, okay? I don't want to do a ton of them because each one of these is going to sort of take some time, all right? But we'll come back and visit some other pieces as well and kind of at the end, hopefully have some time to actually practice using that table, okay? So for these examples, 5, 6, and 7, and 8, we're not going to be doing these using the formal definition. All right, we'll be sort of front loading that piece up top here. All right. So again, for that homework, I did ask you on one question to use the formal definition, but most of the other ones, I just want you to use the table. Okay. All right. So let's see. We have the Laplace, this time of e to the at. And we're going to assume that a is a constant and a is not equal to 0. Okay, so we're assuming a is a constant and a is not equal to 0. So if we looked at the table, it would tell you a certain answer. But I'd like us to think about where that certain answer comes from. Okay, so let's apply this formal definition. The formal definition says I'm going to take the integral from 0 to infinity. And it is e to the negative st times the function that I'm taking the Laplace transform of, e to the at. So last time I just had a 1 in here, so I put a 1 into the formal definition. But this time I have a different function. Oh, it spells eat. I didn't even see that. But this time we're replacing it. Whatever that inside function is, that's what goes into that formal definition. Okay. All right, so let's see what this gives us. We're gonna do two things at one time here. All right, so we're gonna go ahead and take our limit as n approaches infinity. We're gonna change the bounds from 0 to infinity to be 0 to n. And then you tell me, knowing what you know about exponents, how can I combine this function here to be a single function of e rather than multiple functions of e? Yeah, we could go ahead and add the exponents, right? We have the same base, thank goodness. Well, we have the same base, e, in both of them. And so I could really say negative st plus at, right? I want to do that, but I'm going to also say that both of them have a t in them. And so really I have a minus s times t dt. Okay, let me just re-explain where all these numbers came from. Negative st plus at, but since they both have a t, I factored out the t. And then instead of writing negative s plus a, I just wrote a minus s. Right. Now let's integrate. We're going to keep that limit n approaches infinity. We're going to integrate and we'll use u sub here. We'll end up with 1 over a minus s e, well, e to the a minus s t. We're plugging in n, we're plugging in 0. Okay. All right. That gives us the limit as n approaches infinity of, let's see, we're going to plug in the n everywhere we see a t first. So 1 over a minus s e to the a minus s n. And the next thing we're going to do is plug in a 0. We know e to the 0 is going to give us 1, so we're just subtracting 1 over a minus s. Okay. All right, now like before, whether it converges or diverges is going to depend on sort of the value of a minus s, right? Before it was just c, but now it's whatever that value is, we're going to say that's going to help us determine whether it converges or diverges. So if a minus s, like that whole quantity, is less than 0, then the function converges to -1 over a minus s, right? So kind of as we saw before, this part is going to go to 0. And so we'll be left with the -1 over a minus s. However, if a minus s is greater than 0, then the function diverges. Okay, so the Laplace is only going to be defined for certain values of a and s, all right? All right, let's do one more question the long way. Okay, this will be the last question that we have to do the long way, all right? Beyond this and beyond that one question on the homework and maybe a question on the test, we're primarily going to be using the tables to help us out, okay? So we have the Laplace of sine of AT. And again, we're going to say that A is a constant and A is not equal to 0. All right, that's our working assumption with these. So A could be a number like 2 or 5, but it's not 0. Okay. So let's apply our formal definition. We're going to say the integral from 0 to infinity of e to the negative st. Remember, that's part of the formal definition. And then we multiply it by our f of t. And so our f of t here is sine of at. And so we multiply by sine of at. All right, now in order to integrate this, we are going to need to use integration by parts. And in particular, because it's sine, it's like a trig function, and it's an e function, we're actually going to need to use integration by parts twice, okay? So let's just kind of write that out for ourselves. We'll need to use integration by parts twice here. All right. And I will say that most of us have been doing an outstanding job on exams showing me all of those steps. I know that there's a lot of scratch work that gets put into your homework that maybe doesn't make it to the exam. But if you've lost any points because of that, I would just make sure you're showing extra steps on that exam, okay? Do everything you can to prove to me that you know what you're doing and that you're not just copying from, I don't know, someone else, a website, whatever it might be. Show me that you understand how to do these processes, okay? All right, so let's get started with our integration by parts, all right? I always like to set up my u, my du, my dv, and my v. And so I should probably leave myself a little bit more space here. But in these cases, depending on what you choose for your u and dv, there's a little bit more choice because it is exponential and trig. But anytime you see like a polynomial, that would definitely, most likely, be your u. Okay, so in this case, I'm going to choose the e as my u. So e to the negative st, which means that the rest of this sine at dt is my dv. All right, you could choose to set this up differently. Different websites or resources might switch the order of those. And this is sort of the one exception to integration by parts where it could be either way and it would be okay. All right. My v in this case is going to be -1 over a cosine of at. And my du, I'm just going to use chain rule down here. I get negative s e to the negative st dt. All right. This is sort of a nightmare of letters here, right? S's could look like fives, T's could look like plus signs. U and V can look so similar if you are a little bit sort of sloppy in your handwriting, right? This is why my U's have a tail and my V's do not have a tail, right? A lot of this has been tailored to be preventative of mistakes that might happen in a problem like this, okay? So anyway, we take all of that, we go ahead and we put this into our, let's say this is our first integration by parts. We go ahead and we put this into our integration by parts formula, and we end up with the integral from 0 to infinity of e to the negative st sine at dt. That's my original, is going to equal, I might not have enough room. Let me do this. It's going to equal uv minus the integral of v du. So we get negative 1 over a e to the negative st cosine at, that's my uv, minus the integral of v du. And so I'm going to pull the s and the a out to the front. All right, so that's just this s and this a. And then what's left on the inside, I end up with e to the negative st cosine of at dt. All right. So now I'm going to cheat. I think this does fit. We'll go ahead and put this right back over here. Okay. So when I plug this all into my integration by parts, this is what I get. And sometimes we only write like the right-hand side of our integration by parts. And with the cyclic ones, like the ones where we have to do integration by parts more than one time, it is useful to write out that left-hand side so that you can sort of combine quote unquote like terms at some point, okay? And so we'll notice here that this first part is absolutely fine, but this second, the integral that popped out of the integration by parts, that I'm going to need integration by parts for again, right? So that's where it comes up a second time. And so let's go ahead and do the setup for that second integration by parts. And I'll go ahead and put it right underneath here. Okay. And so again, I'll set up my u and my v and my du and my dv. So I'm going to keep the same idea. I'm going to have my exponential function be my u. And my dv, therefore, will be cosine at dt. And where did that come from? It came from 1 over a sine of at. All right, so this is where our second integration by parts happens. And so now what I'm going to do, I know this is a lot of writing, okay? We're going to write all of this first clump again, minus that s over a, and then next to it, I'll put my new integration by parts. And I'll put that part in brackets so that we can see very clearly where it comes from, okay? So we've got the original question, integral from 0 to infinity of e to the negative st sine of at dt equals the first part we saw, negative 1 over a e to the negative st cosine, cosine of at minus s over a. Okay, so we've set up everything else we need to write. We're going to open up some square brackets, and inside of that brackets, we'll put our new integration by parts that we have from this pink number 2 over here. And so uv from this number 2 is going to be 1 over a e to the negative st sine of at, right, minus the integral of v du. All right. Now I notice here that I have the 1 over a and the negative s. So I'm actually going to bump those right out to the front of my integral symbol. And that'll be minus minus, which makes this a plus, s over a, the integral of e to the negative st sine at dt. Okay, so there we have our shocking line of all letters. I think there's a few numbers sprinkled in there, 1, 0, right? But all of these letters, we really need to make sure that we're very careful about this step, right? We can see where it might cause some problems if we misassign somewhere. That's a really great question, Kiki. So I'll tell you why I didn't use tabular here, right? Because tabular is definitely way faster when we have the cyclic. So tabular method only works when u is a polynomial, right? Because with the table, at some point, it has to end, right? And so if we have like x squared, then the next line is 2x, then the next line is 2, then the last line is 0. And so that's sort of how we know to stop. But if we think about u being an exponential, it's going to still be exponential, exponential, exponential. Your table's never going to end, and then you're going to be like super sad about it, right? So I have seen that on some exams or on some assignments. If your u is a polynomial, 100% I would use tabular. I would never do this if I didn't have to, right? But we're sort of, our hand is forced here just to kind of practice all of this. So yeah, cool. Okay, so what we're going to do now, we're going to keep grinding through the algebra. We're going to take this negative s over a, we're going to distribute it to the two things inside of the brackets, all right? And so I'm going to go ahead and recopy this over. All right, we've got our integral from 0 to infinity, e to the negative st sine of at dt equals negative 1 over a e to the negative st cosine at. So that part is fine. Now I have to distribute. So I've got negative s over a squared e to the negative st sine of at. And now when I distribute this other one, I'm going to get negative s squared on the top, a squared on the bottom. Integral of e to the negative st sine of at dt. All right, so all I've done is distribute. Maybe I'll make those symbols here. Okay. So the reason why in this more than one step integration by parts is really valuable for us to continue to write that left-hand side is because now it turns out we actually have a like term on the right-hand side, right? I dropped my bounds here. I'll put those back in, right? But we have one of these integrals on the left-hand side, and we have negative s squared over a squared of that integral on the right-hand side. So we're going to take the one on the right, we're going to add it to the one on the left, and we're going to factor out this common integral. And when we do that, we're going to end up with 1 plus s squared over a squared. That's how many of these integrals I have. And then the rest that part stays, right? So the only thing we did here is just sort of combine like terms on the left-hand side. Now, I know I still have a bound of 0 to infinity, right? But since this is an improper integral, we know that we would be effectively going from 0 to n, and then taking the limit as n approaches infinity later on. And so what we're going to do here, we're going to keep this left-hand side for right now. The one change we're going to make is we're going to say that that infinity becomes an n. And we're going to say the limit as n approaches infinity. All right, so we're not changing the problem. We're just saying this is how we handle improper integrals. But what that means on the other side is we're going to take this whole long messy thing. We're going to plug in n. We're going to plug in 0. And we're going to subtract those like we do with any other integral, definite integral. And we're going to evaluate very carefully. And we're going to see what stays and what changes. And so what we're going to find, all right, is that this e to the negative st is actually a common term to both, as well as a minus sign. So maybe before I start plugging things in, let me say negative e to the negative st. What do we have left? We have 1 over a cosine of at minus s over a squared. Plus sine at, evaluated from n and 0. Now, all of this on the right-hand side, we're going to go ahead and plug in an n everywhere we see a t. We're going to plug in a 0 everywhere we see a t, and we're going to go ahead and subtract those two. All right, let's be really careful about this. Negative e to the negative sn, 1 over a cosine of a n plus s over a squared sine of a n. Okay, so I plugged in the n everywhere. Now I'm going to plug in the 0. So minus the negative, we'll make it a plus, e to the 0, 1 over a cosine 0 plus s over a squared sine of 0. And now we get to get rid of a lot of things. This is the worst line, okay? So if you're still with me here and you haven't run away screaming from your computer, this is good. Things are gonna get a lot better now. And in particular, let's start at the last line. Sine of 0 goes to 0. Cosine of 0 goes to 1. E to the 0 goes to 1. So that whole back end clump actually simplifies very well. Now check this out though. If we're thinking about n approaching infinity, e to the negative infinity, that actually gets really close to 0. And 0 times something is going to give us 0. What that means is that our entire left-hand side, grabbed an extra 0, our entire left-hand side, the only thing that is left on that right-hand side is 1 over a, right? All right, we are so close to being done with this problem. Okay, we are still close to being done. All we got to do is we're going to take this 1 plus s squared over a squared, and we're going to divide it to the other side. All right. Now, let's see what that gives us. The limit as n approaches infinity, integral from 0 to n, e to the negative st sine of at dt equals 1 over a divided by And I'm going to go ahead and take this 1 plus s squared over a squared. I'm going to turn that into a single fraction. So I'm going to divide by a squared plus s squared over a squared. All right. Now, hopefully we remember when we're dividing by a fraction, we go ahead and we multiply by the reciprocal, right? So this is equivalent to a over s squared plus a squared, right? All that work we did, at the end of the day, after doing integration by parts twice, being really careful about plugging numbers in, taking that limit as n approaches infinity, we found out that the Laplace transform of a sine function is a over s squared plus a squared. Okay, so in other words, this is the Laplace transform of sine of at. Right. Now again, this is something we're going to see on a table. You're going to look up a table and it's going to say the Laplace transform of sine of at is a over s squared plus a squared. I will not ask you to do all of this on an exam, right? That is not a good use of anyone's time, mine included, right? But I think it is important for us to understand where things come from. And by understand, I mean, let's see a derivation one time. Let's grind through this so that we can have an appreciation for why this table is so fantastic. Like somebody else sat and went through all of these derivations so that we could have a table so that we wouldn't have to do this. And we could focus more on exactly that question that was asked earlier, which is what are Laplace transforms? What do they do? Okay. So we've got about 17 minutes left, which is perfect timing. Okay. Perfect timing for us to now take a little bit of a breath. Say, thank goodness I don't really need to do this formal definition that much. All right. We're going to look at a little fact. We're going to pull up a table. The table, by the way, is hyperlinked into that Google Docs. You should be able to open it right up. It is the link to the one on Paul's online notes. But there are other Laplace transform tables out there. Okay. So this is the one I've chosen to link here just because I know a lot of us have been using that as a resource already, but there are other tables out there. You're welcome to Google your own if you want to. But before we open up this table, I just want to talk about one really important fact that comes out of something being a transform, okay? So I actually want to write a separate one up here, which is that transforms preserve something called linearity. Okay, transforms preserve linearity. You actually know some examples of this. One of them is this. Let's say I asked you to find the derivative of x plus x squared. All right. So I know we've just taken our math to a whole nother level on that previous page, but let's bring it back down for a moment. What's the derivative of x plus x squared? Don't be shy. I know you know what this is. Yeah, it was just 1 plus 2x, right? There's no trick question here. It's 1 plus 2x. But another way we could say that is that we took the derivative of x and then we added it to the derivative of the x squared, right? You've used that rule so much that we almost forget that it's a rule, that idea of being able to take the derivative of separate pieces and then combine them back together with the same sign that was in between them earlier, right? So this plus sign, this plus sign, this plus sign. Now, if you tried to do this with multiplication, then you got yourself into a world of trouble, right? Because one of the rules we talked about at the beginning was that product rule is actually different. Like I don't take the product, the derivative of this term, the derivative of that one, and then multiply them together. That's like the very first thing you learn about product rule is don't do that, right? So this idea of linearity is actually really special to addition and subtraction. Similarly, if I said, find the integral of x plus x squared dx, you would say, well, that's the same as finding the integral of x dx plus the integral of x squared dx. And this was such a common rule, we never really took the time to write it that way. And we would end up with x squared over 2 plus x cubed over 3 plus c. Right? So derivatives and integrals are transforms, and transforms have a special property called linearity. All right, and maybe that was something that you remember from linear algebra, but this linearity basically means that you can add and subtract and multiply constants without that having to be a big deal. Well, it turns out that since we're talking about a Laplace transform, right? That's our fancy symbol there, the Laplace transform, the same ideas apply. If I have a constant A and a constant B, and then I have two functions here, I can actually take the Laplace transform of one, take the Laplace transform of the second one, and then add them back together. Okay. And so that's where we're really going to be looking in these last few practice problems, is applying, like practicing using the table and thinking about this idea of linearity, that even though like we look at example 5, it has so many terms, all we're going to need to do is look up every single one in the table. Okay. So let me give you a moment to actually open up that table, and let me go ahead and pull that up on my screen as well. Now, I think this is sort of, have not ever practiced sharing a split screen before, so we're not going to do that right now. But I'm going to ask you to pull up that table of Laplace transform. And if anybody's having trouble accessing that, please let me know. I'm going to go ahead and drop the link in the chat as well, so you can directly access that in case the Google Doc isn't working for some reason. All right. Is there anyone who is not able to find that table? Let me know. I don't always want to assume that silence means that everything is fine, but I'm sure you would ask if you needed to be able to access that. All right. All right. So if the question says find the Laplace transform, and it does not say use the formal definition, I mean, you are welcome to do something like this, like we did for example 4, but my guess is nobody wants to do that again. So we're going to go ahead and just use that table. Okay. So let's go ahead and write this out. All right. So if I were trying to find the Laplace transform of f of t, so 6e to the negative 5t plus e to the 3t plus 5t cubed minus 9, what linearity tells me is that I can say 6 times the Laplace transform of e to the negative, okay, see, this is where it starts to be tricky. That's a 5, right? So minus 5t plus the Laplace transform of e to the 3t plus 5 times the Laplace of t cubed minus 9 times the Laplace transform of 1, right? So that fact that we saw above, which I said is called linearity, means that we could find each one of these and then string them all back together. And if you'll look, you should be able to find each of these on the table, right? You just have to be really careful about plugging things in to the formula you see on the table, okay? Sign mistakes here, like a positive, negative, are costly. All right, so if we were in class, I would ask you to tell me what the Laplace transform of e to the negative 5t is, all right? Since we are not live altogether, if you look at your table, this is number 2 on the table, right? And it says that the Laplace of e to the at is 1 over s minus a, right? What is our a value in this first function that I'm trying to transform? Yeah, our a is a negative 5, right? And so we have a is negative 5. That means I'm going to have 1 over s minus negative 5. S minus negative 5, right? So we're going to go ahead and say that that's 1 over s plus 5. All right. And so let me actually go back and write my s and 5 again, right? So s and 5. So I know that those are different, right? Okay. What is my a value for the second function that I'm trying to transform? Yeah, it's 3. So that's going to be 1 over s minus 3, right? Okay. Plus, all right, now we're going to look for a different line on the Laplace transform table. In fact, we're going to be looking at line 3 on the table, right? And again, it's important that we can identify our n, where n equals 3 in this case, because we're looking at t cubed, right? So the Laplace transform, I'm still going to have my 5 out in the front. And that t cubed, the Laplace transform is n factorial, right? In this case, n is 3 over s to the n plus 1. All right, minus 9 times the Laplace transform of 1 is 1 over s. Okay, so it's not a terribly complicated technique, right? We're literally using the table, we're rewriting it. But if we wanted to clean things up, we could certainly write 6 over s plus 5 plus 1 over s minus 3 plus 5 times 3 factorial over s to the 4 minus 9 over s would be perhaps a better final answer. All right. So not too bad. We really just have to find the correct line and plug in the correct numbers. Okay. All right. So let's take a look at question number 6 over here. Okay. So let's take a look at question number 6. We've got 1, 2, 3, 4, 5 different functions. All right. Some of them are our regular trig functions, cosine, sine, cosine, sine, but one of them is one of our hyperbolic trig functions. Okay. And so sine with an H on the end is not a typo, right? It's not a typo. And it can be pronounced one of two different ways. Okay, so some people pronounce S-I-N-H as cinch. Okay, other people pronounce S-I-N-H as shine. Okay, so some people call it cinch, some people call it shine. I know that neither of those is maybe what you would think it is, but cinch and shine are two of the most common. I actually don't know if there are other ways to pronounce that. Okay, so if you hear someone say cinch or you hear someone say shine, they mean sign with the H on the end or the hyperbolic sign. Then if you scroll down to the bottom of that table in Paul's online notes, you'll see a definition of what shine or cinch is defined to be, okay? But the same rules apply. We got to go ahead and separate them all, and we're going to use our table to find each one, okay? And so let's go ahead and write this out. So if I do the transform, it's not going to be lowercase g of t anymore. It's going to be uppercase g of s, right? All of the t's drop out. I only have s's at the end. So I'm going to end up with 4 times the Laplace transform of cosine 4t minus 9 times the Laplace transform of sine of 4t plus 2 times the Laplace transform of cosine 10t plus 3 times the Laplace transform of sine 2t or sinh 2t plus 3 times the Laplace transform, oh, that's an ugly one, Laplace transform of sine of 2t. Okay. All right. Everybody pick your favorite one. All right, there are 1, 2, 3, 4, 5 of these and about 6 of us in the room. So maybe pick one, type in what you got from the table. All right, what did you get from the table when you plugged in the numbers for N or for A? All right, and I'll start writing these out, but I'll write out the simplified version, okay? Good, 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 good. All right. Yep, I agree that that's what I got for the shine one as well. All right. And hopefully the rest of these all match up with what you get. All right. Now we are out of time today. I want to respect your time. There are 2 more examples right here that you can practice. There's a bunch on Paul's online notes if you want to just practice using the table more, right? It's not like using the table is not necessarily a challenging skill. It's more just, did you get all the signs right? Did you plug in the right number for N or the right number for A? Okay, so it's more of an accuracy piece rather than like using the table as actually, excuse me, complicated. Okay, I don't think it's complicated. It's certainly not as complicated as our series solutions that we were looking at last week, but it's just something we really want to be able to be accurate on, because beginning tomorrow, we're going to actually start to think about how we go backwards on this table, right? So we're moving very quickly through this idea of like, sometimes we go in one direction and sometimes we go in the other direction. So take some time today to sort of practice using that table. I think maybe even just like 15 minutes would probably be really helpful. Okay. All right. So that is all we have time for today. I'm going to go ahead and stop the recording.